good time to start. Okay. So this is a long talk in this program by Dominic. I think he has a new title. But I want to mention that this kind of Blackboard talk was designed to have a lot of discussions and questions. So please, ask questions. And, let's welcome Dominic.
Yeah, thanks. So I have a lot of stuff to talk about, but I'd rather answer questions and get through everything, so I hope people will ask questions. So yeah, the new title of my talk is Let's Get Loopy, because I'm going to be talking a lot about loops. I'm going to talk about Floquet topological phase, and loops really is the key concept to understand them, and we'll see how that comes about. Right, so traditionally we would talk about topological phases in stationary systems. So we have some Hamiltonian H, some stationary Hamiltonian, and then we can consider maybe the zero temperature phases. That is the ground state. And we know that the ground state of a quantum system, many-body quantum system, can have many interesting phases, including topological phases. But here I want to talk about a topological phenomena in a different setting. So instead of some Hamiltonian H, I have some time-dependent Hamiltonian H of t, but it's periodic, so there's some period capital T, and Hamiltonian comes back to itself after one period. So you're driving the system at some frequency. Apply some time varying time oscillating magnetic field, for example. Or in cold atoms, maybe you have more control over Hamiltonian. You can just do different divider. And just, as a function of time, just apply different Hamiltonians in such a way that it's time periodic. So we call this a Floquet system. Right, so in a Floquet system, instead of a continuous time evolution generated by H, you can imagine that there's a discrete time evolution generated by the time evolution of a one-time period. So if we define the Floquet unitary, it's a unitary operator, and then at integer multiples of the driving period, the dynamics are generated by taking powers of this UF. So this UF really is the key object in the dynamics. And then if you want, we can say that the eigenvalues of this operator, the unitary operator, so we can write them as a phase factor, E omega times capital T. So this omega is called the quasi-energy. There's units of energy, but it's different from energy in the sense that omega is the same as omega plus 2 pi over t. So in a Floquet system, because you have only this discrete time translation symmetry rather than the continuous time translation symmetry, the eigenvalues are periodic. Just as the eigenvalues of a discrete translation operator live in the Brillouin zone. So we have periodic energies, if you like, periodic quotient. So in particular, this means that the Floquet system has no notion of the ground state. This, the quasi-energies live in a circle, so there's no notion of the lowest energy, because it can always wrap around the circle. So this raises the question of if we want to classify topological phases, what do we really mean? Because obviously, for stationary systems, we talk about the ground state. For Floquet systems, there's no really notion of ground state anymore. So this goes back to the fact that these phases are really going to be non-equilibrium phases of matter. Here we're talking about phases of matter in equilibrium, but Floquet phase is necessarily going to be a non-equilibrium phenomenon. So there's really two different avenues we can go to define phases in the absence of a proper ground state. So one of them is notion of quasi-ground state. Or maybe even just quasi-stationary state. So the claim is in some regime of a Floquet system, if a Floquet system doesn't really have a proper ground state, and maybe define some regime, some approximate ground state, or even just some state that approximately stays stationary as a function of time. And then you can try to classify phases in that kind of a stationary state.
These quasi-ground states, any eigenstates can be called quasi-ground state. Because it's hard to know which one have the lowest energy, whether any eigenstate.
In some sense, yes, but the problem is that in a Floquet system, generically the eigenstates are thermalized states available like the infinite temperature, so any trace out any subsystem is a maximally mixed state. So the eigenstates of the Floquet system, with the exceptions that I'm going to talk about soon, are not really the states you want to consider because they're just boring states. So that's, in some sense, maybe you want to consider approximate eigenstates, which are not true eigenstates. But there's another direction you can go in which you can consider, instead of phases that matter in some stationary state, you can consider dynamical phases. So dynamical phase is saying, instead of looking just at some state, we look at the time evolution of a Hamiltonian under an arbitrary initial state. So we consider just some arbitrary initial state. If it's not stationary, it'll have some time evolution under the Hamiltonian. And then this dynamics can have like sharply distinct properties separated by phase transitions. So we can try to classify dynamical phases in this sense. And so an example of a dynamical phase, which maybe you're familiar with, is the distinction between a many-body-localized phase or an ergodic phase. The NBL phases versus ergodic phases, the dynamics for a generic initial state can look very different. But I'll come back to this in more detail later. So what I want to do first is I'll consider in this kind of phenomenon where you have some kind of quasi-stationary state, and show you in the simplest case, which is free-fermions, how you get new topological invariants. So I want to do free-fermion case 2 because it's very concrete. Then we'll move on to the interacting cases, which are much more subtle. So let me just briefly remind you about how free-fermion classifications work in stationary systems. So if you have some free-fermion Hamiltonian H, then let's assume that's translation invariant, so there's a momentum. And then we can draw bands as a function of momentum. And so the negative energy states are going to be filled at 0 temperature, and the positive energy states are empty. And we say that the system is gapped if there is a finite energy window that separates the empty states from the filled states. And one of the famous results is that Hamiltonians of this form can have different topologies. There are Hamiltonians, free-fermion Hamiltonians, band insulators, which are separated by some kind of topological invariance and cannot be connected without a phase transition. So, for example, a Churn insulator which has some Hall conductance can never be connected to a trivial insulator which has no Hall conductance. So Hall conductance is a topological invariant. So how do we classify free-fermion band insulators? So we want to classify Hamiltonians of this form. So the first step is we can always deform the empty bands and the filled bands so that they're totally flat. Function of momentum, they're totally flat. So now the only information left in the Hamiltonian is a function of momentum, which momentum states are unfilled and which momentum states are filled. So basically what we have is a continuous map from the momentum torus, the Berlin zone, into the space which I can call PMM. So PMM is a space of all possible m-dimensional subspaces in m plus n dimensional Hilbert space. So m, here m is the number of filled bands. N is the number of empty bands. So that's why the filled bands are specified by which states of field at a given momentum, so it's an n-dimensional subspace of the full Hilbert space. So we can also write this is just another way to write the same space. It's in terms of the quotient of unitary groups. And then we want to consider stable spaces. So we want to consider the limit in which the number of filled bands goes to infinity and the number of empty bands goes to infinity. A kind of stable homotopy, if you like. So we set m equals n goes to infinity. So this is the so-called symmetric space. And here I'm doing the classification in class A, so there's no additional symmetry. This is a symmetric space for class A. But anyway, the point is we just want to classify homotopy classes of maps from the momentum torus into this symmetric space.
Why M and N have to be identical?
Well, they don't have to be identical,
Oh,
but
I see.
as long as they sort of grow together, then the resulting space will not be different. So we call this P infinity. And basically the free-fermion classification in class A reduces to calculating the homotopy groups of this space. And so the result is here D is the space dimension. That's the dimension of the torus that we want to consider. Okay, so this is the famous classification of topological insulators in class A. And so this thing, for example, in D equals 2, we have the Z classification. So this Z is the Chern number of all the filled bands. which we know is also related to the Hall conductance. Okay, so that's the stationary classification. Now, yes.
Can you explain again why you consider the case where m is n? Suppose I take m to be k and n to be k squared. I take k to be infinity. Do you get the same result?
I think you probably do. So don't quote me on that, but I think it's. But actually, the interesting case would be what if you set you keep one of them. What if you keep the number of field bands finite, and you set a number of anti-bands to it, which is actually the more physical case, because in this physical system you always have a finite number of bands. So then the question is, do you always get the same result? I think you probably do get the same result. Well, yeah, I'm not sure, but it's kind of funny that people always define the classification this way, even though it's not the physically correct way. Yeah, anyway, so this is the stationary classification. Now I want to tell you that when you're periodically driving the system, this classification gets augmented, and we'll see how that happens.
Question.
Yeah.
And why do you need to take this limit? Why do you need to take a limit of an infinite number of bands?
Well, you don't have to, but physically you want to because you want a stable homotopy classification. You don't want to consider phases which are trivialized just by adding more bands, because physically, like, you always have more empty bands available to you because the energy of the electron is unbounded. So physically there's always an infinite number of empty bands. And field bands, maybe you only have a finite number, but usually you can. Usually you have a finite number of field bands available to you because you have electrons tightly bound to the ion cores. So you can always take those and then try to use them to trivialize the state. So you want to consider the classification which is stable with respect to adding extra empty bands or extra field bands. I mean, there may still be some interesting physics contained in doing a different classification which is not stable. You had a paper which just came out recently about that. But that's not the way people traditionally formulate the classification. Right, so now I want to tell you about the new invariants that come up when you have periodic driving. So remember, periodic driving, we have some time periodic Hamiltonian. So this inverse Hamiltonian is still free-fermion and translation invariant in space. So we can define the Floquet operator. So again, we have a notion of bands. So now we plot the quasi-energy as a function of momentum. So we have various bands. So unlike in a stationary case, you don't really have a notion of negative energy states or positive energy states, because in fact, the quasi-energy is periodic. So you have like pi over t and minus pi over t. You have to identify these two quasi-energies. So this axis lives on a circle, basically. But suppose, and I'm not going to say too much about how you would realize this, but suppose you can have a quasi-stationary state, build some quasi-stationary state, which is basically characterized by the fact that you have one band or some set of bands filled, and then the other ones are empty. And I'm going to assume that the field bands are separated from the empty bands by some quasi-energy gap. And so now I'm going to classify the topology of Floquet evolutions characterized by you have a filled band separated from all the other bands by quasi-energy gap. So how do I do this classification? Well, first of all, because the quasi-energy is periodic, I can always move all the empty bands to the top of this picture, because I'm just basically using the periodic topology in this axis. So now all the empty bands will be at the top, and all the filled bands will be at the bottom.
You're okay doing this process even if a filled band needs to cross an empty band? If they're
The
like-
filled band shouldn't cross the empty band because then the gap.
Okay, so you need to maintain the gap.
Yeah. But I mean, like, the empty band goes around this way, so it doesn't cross the filled band.
But even if they're like empty filled, empty filled, empty, it's okay too. If you have like multiple gaps.
Then you might be in trouble. Let me see. Case. I mean, there are ways to make bands cross to each other, which actually doesn't. Just focus on the case of the bands rolled together. Okay, so now we can flatten the bands again. So this picture looks the same as here now. In fact, we can, once we've written in this platform, this Floquet evolution operator is just the exponential of a time-independent Hamiltonian H. It's just this flat band Hamiltonian. This flat band Hamiltonian, and now you take the exponential, it's still a flat band unitary, and the effect of taking the exponential of this is that the quality energies get identified like up here and down here, but that doesn't change anything. So this Floquet evolution operator is just a time evolution of a static Hamiltonian. So you might say, okay, well, now we've just returned to this case, and so we only have this invariant. But it turns out there's actually another invariant you can define, okay? And let me explain why. So we can. So here's the point at which we start getting loopy, as the title suggested. So I'm going to define a new thing, u of t, which is the time-ordered exponential, but only from 0 to t. So this is the generative evolution from 0 to t. And so clearly, obviously from this definition, you see that u of naught is just the identity. And also u of t is a Floquet evolution operator. Given this definition, that's clear. But now we can look at what happens at intermediate times. So we know that we have a path from the identity. It's a continuous path in the space of unitaries from the identity to UF. But the point is that given two Floquet evolutions, each of which satisfy this condition, there may be different ways to get between here and here. So you could go like this, but you could also go like this. And so the interesting thing happens is, what if these two paths are not homotopic? What if this path cannot be continuously deformed into this path? There's some obstruction in the middle which prevents it from deforming one path into the other path. So this is how you get non-trivial Floquet phases, which are distinguished by different kinds of invariants. They're distinguished by which path you take to get to the evolution up to one time period. So if you like, you can say that these phases are distinguished by their micro-motions. You know that after one driving period, you have a certain time evolution, but in the course of a driving period, the electrons are doing something. So this is kind of a short-scale micro-motion of the electrons. And so these can be topologically distinct. So whenever you have two paths which are topologically distinct, or any two paths, by reversing one of the arrows, it basically defines a loop in the space of unitaries. So this is a map from the circle into the space of unitaries. So this is what we call a loop.
Sorry, by unitary you mean there's some locality involved, or just most general?
Right, the space of unitaries which can be generated by, in this case, local free-fermion Hamiltonians. So now what we need to classify is we need to characterize these loops. So in the free-fermion case, actually, this is pretty straightforward. Because we have translation invariants, so we can work in momentum space. So what we have basically is a map from S1, and then we also introduce momentum dependence from the Berlin zone into U plus N. This is just, remember that M was the number of empty bands, and N was the number of filled bands, so N plus N is just the total number of bands. And so generally, in any given momentum, the most general possible unitary is the unitary that mixes up all the bands. So this is the unitary group. The group for unitary is actually on the N plus N dimensional Hilbert space. So again, we want to consider stable homotopies, so we'll send N to N to infinity. So we sort of have the infinite unitary group. And so we have this. So we have this map from the d torus, which is Berlin zone, and also the circle, which is the it's a time parameter. But of course, this S1 times the d torus is the same as the d plus 1 torus. So really, what we care about is the d plus 1 homotopy group of this infinite unitary group. Okay. So what is the answer to this? You can look it up on Wikipedia or whatever. Z is even, and 0 is d is odd. Actually, this is the same classification that we got from the stationary case, but these are a new kind of invariants because they're not distinguished by stationary invariants, which are determined by this endpoint, and it's the same in both of these paths. It's a new invariant. So basically, for example, in d equals 2, you know, the original Z classification is going to get augmented to C times C. So what is the interpretation of this new invariant? Well,
why don't you quotient out the UN? Because of the field band, and the choice basis will not be important. You know, in the previous case, you quotient out UN and UN.
Well, that's because I was really classifying the set of subspaces. But here I'm really classifying the unitaries.
But when the unitary act on the field band, whether there is something, there's some unitaries like changing the basis of field levels, and those unitaries seems to do not have a trivial action because those levels are field, so the range rotation among those field levels do not change the many-body wave function.
Well, they have trivial action on the state, which is the field state. But in some sense, we want to be more general and consider the action of this unitary on any initial state.
Oh, I see.
So maybe in this like a language where whether you have which band field is not important. That is not
Any arbitrary feeling.
It's not presented in this.
Yeah, well, in as much as, in some sense, so this endpoint here is specified by, in this endpoint knows about which band is filled, but we sort of don't worry about the endpoint anymore, we just worry about classifying homotopy classes of loops. I suppose you might worry about whether, given the loop has to go here and then come back, whether that is more restrictive than just classifying the homotopy class of any loops, which sort of goes anywhere. But I think that's not the case. It's get over homotopy class of loops, even this requirement.
So how the final this UF know which band are filled? So maybe you define below the eigenvalue below like omega in the omega minus smaller than 0. You define.
Well, just because we already deformed the unitary so that it's this flat band of +1 and -1. Okay, so maybe the entity doesn't know which one is filled, whether the +1 fills or -1 filled, but it definitely knows that there's a difference between the two.
Is there not some worry about, the closing a gap, right? Because we're just moving, or we're just looking at the space of homotopies of maps from D+1 towards the unitary matrices with no restriction on keeping bands separate as we're moving through for these loops.
Right. Well, there's no notion of gap comes from quasi-entity, and a quasi-entity is defined with respect to the discrete equation of the one-time step. So if you're not considering just the evolution at models of T, there's no notion of gap to even define, let alone say apply it as not zero. Okay, so we want to say what is the interpretation of this mu z invariant? So there's this, really nice paper by Rata and Al, which gave the interpretation, or one interpretation. There's many ways to think about it. So the idea is to suppose you consider a two-dimensional system but with boundary, a real space boundary. So it's a real space picture. So you have your two-dimensional Floquet system, and then now you have a boundary. Saying that we have a 2D slab, but as a 1D boundary. So you can consider the same time evolution as before, but with the Hamiltonian restricted to this space with boundary. And then you can say, what does the spectrum look like? And so you have your bulk bands. So you have your states which come from the bulk, and these are basically these are basically the same even with boundaries the states of the bulk. Then you can also have edge states, which are states associated with electrons that are moving near the edge. So the edge states will kind of exist, the quasi-entities which were not present. This is kind of the gap, the quasi-entity gap. Quasi-entity gap. So if even though you have this quasi-energy gap in the bulk, in the boundary, you can still have edge states living in the quasi-energy gap. And so it turns out that so you can imagine that the edge states are going to be filled up to some. If you fill in the bulk electrons, then you also fill in the edge states, but only up to some cutoffs. And so what we're showing in this paper is that the Chern number of these bands, which is a stationary invariant, is given by, so there's two things you can define here. There's the n up, the number of edge states, number of, so this edge state where I've drawn it is chiral because it has group velocity only going in one direction. So I say n up is the number of chiral edge states above the band, and n down is the number of chiral edge states below the band. And so the Chern number of a band is the difference between n up and n down. But even if the Chern number is 0, means whatever chiral edge states at the bottom is, they also have to exist at the top. You can still have chiral edge states which are protected. So for example, if C equals 0, you could still have these pair of chiral edge states, one going up and one going down. So the whole conductance of this system is 0 because basically each of these two edge states contribute oppositely to the whole conductance. But it still has these chiral edge states, which are in particular protected from backscattering because they're chiral. So an electron is moving along the boundary cannot backscatter into the backwards moving state. There are no such states at this quasi-energy. So you have these protected, backscattering protected states moving along the boundary, even without the Chern number. So that's the non-trivial feature which is produced by this new Floquet invariant for extra Z.
Yeah, so I'm always curious about how to realize this. Like, you have some periodical driven system. Somehow you assume there's some regime in which you can realize this a scenario that some bands are filled, some bands are empty. So is there such a, what's the physical regime you're talking like have in mind? Like probably you want to, because if you have like a resonance, the system probably will heat up, right? Very soon, and somehow maybe you're talking about some off resonance, but even that can one prove that such a regime exists?
Well, so in a free-fermion system, it doesn't necessarily heat up. If your routing frequency is large enough, there are no resonances. There are no free-fermion resonances, so free-fermion system doesn't necessarily heat up. It's still the question of how exactly do you make all the electrons sit in one particular band and not one of the other bands. I think like Tim Raphael has a paper where it talks about coupling to a bath and engineering the bath coupling in such a way that it leads to a stationary state that looks like this. I mean, I don't know how realistic this is. In the many-body case, which I'm going to talk about later, it's clearer what you should do. Here, I really just wanted to give an example of the new topology that arises.
Question? I think I missed something very basic. Why do you need to have a gap that separates the field and whether the band is filled or empty doesn't enter the classification?
Well, once you reduce it to a loop classification, classifying loops, then I mean the loop classification doesn't care about that. But in order to get to the idea of loops, first you need to say that you have a given endpoint, and now you want to classify the Floquet evolutions for a fixed endpoint. So defining the endpoint, you have to specify which bands are filled and which ones are empty. Because if all you're doing is classifying, if you don't have this requirement, then all you're doing is classifying unitary evolutions, but you don't keep this endpoint fixed, and that doesn't have any non-trivial topology, because you can always take this and shrink it to 0 and move it somewhere else.
So it's useful to claim that it's only useful to claim that UF is different from identity.
Sorry?
There's a gap. This is only useful to claim that UF is different from identity.
Sorry, can you say that again?
It's the assumption that there's a gap only used to guarantee that UF is different from identity.
It's not that UF is different from identity. I mean, in some sense, if UF was the identity, then it's still different from space. Then you have a loop going back to identity. It's saying that this loop classification is a classification relative to a given set of Jordan empty bands which specify what UF is. So that in itself is not
Can I try to comment? So, so Eugene, like, if UF is identity to start with, that's great because you have a loop to start with, and there's no extra step involved. So the need of the gap is just that if UF is not the identity, then you want to construct some loop that will actually be something relevant to the system. Then you need to find a way to bring UF back to identity in some way. So if you have a gap, then you can define some static Hamiltonian with respect to the gap, because you need to take a log, but the log knows of a branch cut. So that's more like a convenient trick. So that's sufficient, but it's not necessary. So even if you don't have a gap, if you know how to define a path which is trivial and go back to the identity, then that's fine.
yeah, but really what I want to claim is that it's all very well to classify loops, but then I want to say that my Floquet version, I apply perturbations, that this classification is going to be stable. And I think if you don't put any requirements on the Floquet evolution operator after time t equals t, then I don't think you're going to have stability.
I just want to clarify one point. I mean, it doesn't seem that the UF depends on the occupations for the free-fermion case.
Well, it's sort of
Is that-
defined
is
in
that
terms
right?
of the occupations, right?
Okay.
Because UF here is the once assume that we've already deformed everything to the flat bands.
I mean, I could deform it or not. I mean, I guess I don't understand why the construction of UF
The point is
depends
that we
on
want to be able to compare Floquet evolutions which are a different UF, because UF itself is deformable. So if we have one UF and then a different UF prime, there's no way to compare these two paths in a meaningful way. So what we want to do is we want to take whatever our Floquet evolution operator is and then deform it into a canonical form. So assume that this UF is the canonical form, which is the flat band version. And then we can do this thing. And then once we've done that deformation, maybe I should put it like this. Flat band version. Once we've done that deformation, now we can compare the two paths.
Right. But it seems like I have freedom in choosing what form I put UF into.
Well,
Like, I don't see why I need to choose a flat band form. I could just fix it to be one thing and then evolve it so that I end up there one path, and then evolve it some other way so that I end up there a second path. I mean, it seems like it's convenient maybe to put it in a flat band form, but I don't see why it's necessary.
I mean, you need, for this to work, it needs to be a canonical form that applies for a whole class of evolutions. So the way we construct the canonical form is to say that you take all the filled bands and all the empty bands and you flatten them in a certain way. So, I mean, that's the rule that we use to construct this canonical form. Otherwise, we don't know how to do it.
Okay, maybe I can ask you about it later. I guess I don't see why that particular form is needed. Seems like you have a choice to choose any form. And then as long as you stick with it, then it seems like the whole argument would go through.
Yeah, but I don't know how to define the canonical form in a way other than like, in terms of the two bands.
So you mean that if you apply the flat band condition, then the wave is uniquely determined?
Sorry.
Do you say that if you apply the flat band condition, then the wave is uniquely determined?
Well, I define the canonical UF to be the one to be the flat band Hamiltonian, which is plus one empty and minus one filled. That's just how I define it. So given any band structure, that canonical form is defined just by my definition.
Can I confirm one more thing? So to classify static topological phases, instead of saying we are classifying the different Hamiltonians under some symmetry, we can actually say we are classifying different wave functions of the ground states under some symmetry. Then it's totally legitimate to flatten the spectrum and only because the information that we need and the information that's left is the wave function. Here I'm aware that to classify Floquet topological phases, it's also sufficient to consider the eigenstates of the unitary evolution UF.
You mean the eigenstates in the many-body-local space, in the Fock space, right? Well, because in a single particle picture, all of these things are eigenstates in terms of single particle states, but every k you have a set of eigenstates. But I think that's what you mean. I think you mean the eigenstates in the many-body space, the Fock space.
Okay, I actually need to think about the difference, but if I mean that, then what?
So this kind of topology is not determined just by the eigenstate. Some more non-trivial feature of the whole unity that's going on. Later, I'm going to talk about states which are determined just by the looking at the eigenstates, but that's this free-fermion bits and other examples.
Because these are basically the macro motions in the process of the traffic.
Here we're really trying to classify something more. We're going to classify the whole. We were trying to classify the whole unitary. Given the constraint, you have certain filled bands and certain empty bands. So that's a more non-trivial problem than just classifying the motion of the eigenstates.
So just a very quick question. So I think apart from this loop classification, you can talk about the non-trivial loop, but then I think our goal is to classify UF, right? So I try to say there should be a definition of a trivial UF. So what's that trivial? What's that definition is? That.
Sorry, what do you mean? Well, I guess you can say UF is trivial if it's just the illusion of a static Hamiltonian.
Oh, so that's a definition of trivial. Okay.
Okay, free-fermions. I feel like I should have gotten AJ to help me give this whole part, because actually free-fermion phase is not my expertise so much. But I wanted to give a warm-up. But maybe I just obscured things. Let me talk about the many-body case, because that's the case I understand well. Now I want to talk about interacting systems. So interacting systems is kind of a problem. When you have interactions, generically, if you're driving it periodically, the system will absorb energy from a drive. There's no conservation of energy when you have periodic driving. So the system will just keep absorbing energy from a drive. In the many-body system, there's always resonance, which allows it to absorb energy. And so at late times, it'll just heat during the temperature. The idea is we're going to, how to prevent this from happening, we're going to assume that we have many-body-localization. So the idea, and so this ties into the notion of dynamical phases. Because many-body-localization, you can think of it as a kind of dynamical phase. So we take some initial state psi, evolve it over some time, and then see what happens. And so there's two very distinct regimes you can have. There's the MBL regime, and the ergodic regime. So the ergodic regime is T goes infinity, the system keeps doing the temperature in the Floquet case. MBL regime, not only does it not heat to infinite temperature, in fact, there's a complete set of conserved quantities which meet with the time equation. So there's an extensive set of conserved quantities. And so what this means is that in the ergodic regime, whatever the initial state was, the system eventually loses all information about the initial state. It goes to the temperature state. But in the MBL regime, you have these conserved quantities. So whatever the expectation value of these conserved quantities are at equals 0, these are frozen in. The system remembers that forever. So now the question is, inside of the MBL regime, is there distinct dynamical phases? So the answer turns out to be that yes. So for example, if you have an Ising symmetry, then there's these two kinds of MBL phases, the MBL paramagnet and the MBL steam glass. And they're distinguished by the dynamics of the order parameter. So if you define a magnetization, which is an order parameter for Ising symmetry, then for a generic initial state, in the MBL spin glass, that magnetization will get frozen in. Whereas in the MBL paramagnet, so this is a function of time. MBL paramagnet, even though you have these local conserved quantities in an MBL system, in the MBL paramagnet, these local conserved quantities are actually orthogonal to the magnetization. So the magnetization actually go to 0 at times. And so these are distinct regimes of this MBL system separated by phase transition.
Excuse me. But since you have a local conserved quantity, whether for every MBL state, you can find a local order parameter which became constant, just like the Ising case.
Well, the point of an order parameter is that it has to issue the anti-commute of the symmetry. So we impose a symmetry, which is the Ising symmetry. For something to call something an order parameter, it should get flipped by the symmetry.
Okay.
So in the MBL's paramagnet, you cannot. There is no such order parameter satisfying that property, which remains non-zero.
I see.
So in the MBL paramagnet, the late time state really is symmetric under the Ising symmetry, so it doesn't spontaneously break the symmetry.
So, yeah, I see. I think so. When you have when the microscopic Hamiltonian have a symmetry, maybe the order parameter. There is no such order parameter on that commute with the symmetry. But because I don't know whether this local conserved quantity can be viewed as emergent.
I mean, people call these local conserved quantities emergent in the sense that I think they kind of well, they depend on the parameters of Hamiltonian. They have like exponential tails, so so that's what people mean by calling them emergent. But so what was the question?
Yeah, I just wonder whether there's always an emergent symmetry and there's an associated order parameter for this emergent symmetry.
That's probably the case. If you define emergent symmetry that depends on the parameters of the Hamiltonian and sort of requires a quasi-local unitary to make it local, then there probably always exists an emergent symmetry. But I think the more interesting case is where the symmetry is microscopic to begin with, which is the case I've talked about here. Okay, so we established that there are different MBL dynamical phases. Okay, but how do we classify these phases? And so an idea of how to do that is we use the fact, so it turns out in the MBL regime, eigenstates, so here I'm talking about eigenstates of the Floquet evolution operator, or the same thing happened in the stationary case with eigenstates of a Hamiltonian. Eigenstates look like ground states. What do I mean by look like ground state? I mean that I can actually define a fictitious Hamiltonian if they look like gapped ground states. I can define a fictitious Hamiltonian such that these eigenstates actually are the gap ground state of that Hamiltonian, and it's going to be a local Hamiltonian. Now that Hamiltonian doesn't have any physical significance, but it shows that the eigenstates of MBL systems must have very special properties. We know that generally the eigenstates of the ground state of a gapped Hamiltonian has very special properties. For example, the entanglement law, the entanglement entropy satisfies an area law. The correlations will decay exponentially with distance. So in MBL system, all the eigenstates satisfy these special properties. So this is very different from the ergodic regime where, in fact, there's a thing called the eigenstate normalization hypothesis. For Floquet systems, it basically says that all the eigenstates look like the temperature state, at least in terms of tracing out subsystems. Trace out any subsystem, and the eigenstate will look like any temperature state. So MBL is very different because the eigenstate look like gap ground states. Okay, but now we can classify MBL phases because we already know that we have a classification of zero temperature phases, zero temperature topological phases, or symmetry breaking phases. And so that classification is really just a classification of ground states because at zero temperature, the ground state is all you have. But now we can apply this ground state classification to the MBL system because all the eigenstates of an MBL system, not just the ground state, Well, from Floquet system, there is no ground state, but all eigenstates look like ground states. So now we can apply the classification and say, take a given eigenstate of this system, it looks like a ground state. What phase does it lie in? What phase is it in according to the zero temperature classification? We classified MBL phases. By the zero temperature phase. So, for example, in this paramagnet spin glass case, the paramagnet eigenstates would look like ground states of a paramagnet, and the spin glass eigenstates would look like ground states of a ferromagnet. So, in particular, they will come in doublets related by the eigensymmetry. But of course, this is more general because we have not just symmetry breaking phases. I mean, zero temperature phases can be topological. You can have a toric code, for example. So you can just classify MBL phases by what phase the eigenstates are in. So we get, for example, an MBL phase, which is characterized by the fact that its eigenstates are in the toric code phase.
In principle, in an MBL system, there can be the case where some of the eigenstates look like one zero temperature phase, where some other eigenstates look like some other zero temperature phase.
Maybe, but I think so. Here by MBL, I could mean fully MBL, which means that all the eigenstates are localized. I think that if there's an eigenstate transition as a function of energy or something, then probably at every transition point the states delocalize at that energy. So then it wouldn't be a fully localized system. I mean, that's my guess. I can't prove that that's the case. But I think in a fully localized system, the eigenstates should all be in the same phase. Okay, but is this the whole story? I mean, everything I said so far will be the same for a Floquet system or a stationary system. But the claim is that in a Floquet system you can have new invariants, new phases. So how does that come back? Well, it's going to go back to this notion of the loop. So what one can show is that in an MBL system, in a Floquet MBL system, you can always write Floquet operators. But here is where we go back to the same discussion as we did before in the free-fermion case. And hopefully I can motivate a bit better this time. So we again define this U of T. So given two Floquet evolutions, which both at integer periodically place of time evolution of the same MBL Hamiltonian, you can again have two topologically distinct paths to get there. So given that we have this MBL Hamiltonian, which has certain eigenstates and they're in a certain phase, there's still some different phases you can have within that class because you have different paths. So what we want to really do is classify loops. space of unitaries, but now it's rather than unitaries generated by local free-fermion Hamiltonians, it's going to be unitaries generated by local many-body Hamiltonians. So whenever you have new invariants that classified as loops, these are going to give you new Floquet phases. And so here, okay, here we're really talking about dynamical phases. So, so we're definitely not talking about just phases that are not defined with respect to a specific state. Dynamical phase is about the time evolution in a generic time evolution of a generic state. So it's a property of the whole Hamiltonian, not just a particular state. So here it's clear why.
Quick question. So, so I can always tune this e to the minus IH NBL times t. I can tune that t from 0 to period big T. So will that
I meant to write
big T? Yeah. So I can tune that from 0 to big T. So that is defined to be a trivial, like a path, or is that the trivial path?
Yeah, there's a path which is just generated by evolving under this HMBL, like a constant Hamiltonian. That's all that quote-unquote trivial path. Although obviously you can still have non-trivial properties, but they will be non-trivial in the stationary sense.
Yeah, sure.
So now in order to generate new phases, we want to generate non-trivial loops in the space of many-body unitaries. So actually this is a very difficult problem, and we don't know the complete answer. In a minute I'm going to make a simplification, but first I want to talk about this really beautiful result where, where a example of non-trivial loop is known. So this is this paper by, I guess it's 2 papers. So what they constructed an invariant for loops in 2 spatial dimensions. So invariant actually lives in log of the rational and the finite classification. To simplify, let me just consider one example of a non-trivial invariant for the for example. And so what does this Floquet, resulting Floquet phase look like? So the idea is you have a 2D system. So it's MBL, it's many-body-localized, so in the bulk, if you do some operation here, there's a quantum information about what your operation that you did sort of grows only very, very slowly. Actually, it's some logarithmic like code. But on the boundary, something else happens. On the boundary, the system is not localized and it has this chiral flow going along the boundary. But unlike, for example, the free-fermion thing which I talked about before, which has a chiral flow of charge, because it has these protected edge states, in this system there's no charge conservation. It's chiral flow of something, but all we can really say is chiral flow of quantum information. So if you do some operation here, then the information kind of about that operation kind of spreads chirally around the boundary. Like it doesn't go this way, it only goes this way. Yeah. And so the boundary is not localized and it can't be localized. This is flow of information in the bulk. Information is basically just constrained to not move. So anyway, this is an example of a non-trivial Floquet phase, which comes from a loop in the space of many-body localization. Okay, so that's a very nice work, but the general classification, in arbitrary dimension of symmetry, we don't really understand at all what that should be for these loops. So now I want to make a simplification.
So without many-body localization, that's impossible to have this interacting Floquet phase.
Well, without many-body localization, then at late times there's heat stream and temperature. So it's not certainly not possible to have this Floquet phase and have it be stable to infinite times. There are cases which I probably won't have time to talk about, but where the heating happens very slowly, and then you can have interesting regimes going on at intermediate times. But this phase in particular, I don't think can be realized in that way. But there are some other ones which can be.
So with many-body localization, this phenomena can happen. That's all.
Alright, so simplification I want to make is rather than talking about loops in the space of unitaries, I want to talk about loops in the space of states. Loops in the space of states are much easier to understand, it turns out. So consider some eigenstate of the Floquet evolution operator. Now I can consider its, so I define psi of t is u of t psi. So it's just the time evolution of this eigenstate. Now after time t equals capital T, the eigenstate, by definition, what it means to be an eigenstate has to come back to itself. So after time t equals t, the state comes back to itself. But in the meantime, it's allowed to do some non-trivial thing, and in particular, it could be some kind of non-trivial loop. But now we're talking about just one state, so it's a loop in the space of states. Specifically, it's a loop in the states of ground-like states. It's clear what I mean by that. I'm not talking about a space of generic states on a many-body Hilbert space, which is, a generic state in a many-body Hilbert space is some extremely entangled state. But these states, I'm talking about NBL systems here. So the eigenstate looks like a ground state, and generally when you evolve a ground state into a local Hamiltonian, it always looks like a ground state. So the loop is the non-trivial loop is in the space of ground-like states. So this is maybe a closer generalization of what I was saying before. For a stationary system, you classify NBL phases by the phase which the eigenstates are in. But for Floquet systems, there's a new thing that you can do, which you can classify they are phases not just by the phase of the eigenset in, but by the loop homotopy class of the loops which the eigensets go through under a time cycle. So in some sense, this is a special case of this general unitary loop picture, because when you have a loop in the space of unitaries, obviously it also generates, you just give it an initial state to start with, it'll generate a loop in the space of states. But a loop in the space of states are much easier to analyze and classify. So the question is, do these loops of eigenstates completely classify Floquet phases? And the answer is no. So this one, for example, is not. You just look at the loops of the eigensets go through, they're totally trivial. But somehow there's still something non-trivial about the whole unitary. So these eigenstate loops are not the whole story, but they're a part of the story. So I think, yeah, I'm running out of time, so I want to just briefly say how do we classify these eigenstate loops. So here I want to go on a side note, I want to tell you about a conjecture of Kitaev. Or at least I think it's a conjecture of Kitaev. I conjecture that Kitaev conjectured this. You kind of have to read between the lines of his talks to work this out. Because he's never published his ideas of this, of course. This is a conjecture about the classification of topological phases with symmetry. So it's a conjecture about classifying SPT phases and SPT phases. Stationary classification here I'm talking about. So omega d here is the space of all ground states. Gap ground states. And VG is this thing called the classifying space. When we have a group G, it is associated topological space that you can apply for the classifying space. If G is discrete, it's in Eisenberg the plane space, where the first homotopy group of VG is G itself, and the higher homotopy group is trivial. But this construction also works for continuous groups G. So the general definition is that VG is EG mod G, where EG is a contractible space. With three actions.
So what is the organic space of what?
Space of all gap ground states in D dimensions. Gap ground states of local Hamiltonians.
Without symmetry.
Without symmetry, yes. Or without symmetry. The symmetry part comes from the VG.
Do you require to be some kind of invertible or not? Don't have to be invertible?
Doesn't have to be.
Okay. Okay, so this is I see. So this might just so omega d is kind of like a topology order, and then this map give you this topology order with symmetry.
So this is a conjecture, but I mean, you can understand all the classification that, as far as I know, like the SPT and SE classification, is all consistent with this conjecture. You just assume certain approximations to what this space omega d is. So I'm pretty sure this is true. Well, I can't prove it. You can actually show for any given state for any given SPT or SET state, there is such a map. The only question is, does that map completely characterize the phases or not? So the conjecture is that it does. But anyway, given this conjecture, we can actually make a really powerful statement about classifying these loops. Because what is a loop? It's actually this loop in the space of states. So a loop is basically a map from the circle into omega d. But it turns out the circle is the same as your classifying space for the group C. So PZ is a circle. Well, to see that, you just know that R, the real line, is a contractible space, and Z acts on integrally by translations, and R mod by action is a circle. So that's why PZ is a circle. So this is why I'm saying we have a map of PZ to omega d. And now if we compare with over here, it's saying that a loop in the space of states is the same as adding an extra symmetry. So loop in the space of states is the same as an SPT or a CT phase. With Z symmetry. So this is a very powerful result because it tells you that if you want to understand loops, then all you need to do is you need to understand the difference between the SPT and SCT phases, and we have very powerful frameworks for understanding that. Group cohomology or group supercohomology for fermions, or this framework of G crossed braid tensor gatherers for SETs. But anyway, so we have very general frameworks to understand that, so that allows us to understand loops as well. I guess it can be a bit more general, but if the states themselves already had some symmetry G, then basically classifying an SPT phases of G times Z symmetry. You can be even more general in this is the case where the symmetry relates states at different times. For example, time reversal will relate the state of psi t to the state of psi minus t. And so then you still have this correspondence, but now this group might not be a direct product anymore. In the case of time reversal, it becomes a semi-direct product. So what is the interpretation of this extra Z symmetry? I mean, roughly it's for time translating symmetry. I mean, because we assume that we're talking about time periodic systems, so there is group time translation symmetry where you translate like integer multiples of the driving period. So it's just like a discrete time translation symmetry. It's not entirely obvious a priori that this thing should just enter into the specification just as an extra symmetry, in the same way as just any other symmetry, but it turns out that is the case.
There's another question. Suppose you have this dg to omega d mapping, which describes the space of some state with symmetry. You can study the pi 1 of that space. If this space give you the same result for the Floquet case. Because the pi 1 is this space of topological state with symmetry, kind of like a loop around that space. So rather than try to say we change the symmetry G to G cross Z, we do the same mapping BG to omega d, but consider pi 1 of that
Consider pi
space
1.
of this map.
I want to space.
Yeah, pi 1 of that space of map.
Yeah, because it's the same as map from S1 from BG to omega d, right?
Yeah.
And S1 is BZ.
I see. So they're equivalent to say.
Plus C.
Okay.
So basically, to the extent that we understand the classification of the phases with symmetry, I mean, it's not totally complete, but we have a very good understanding of that now. We can understand all these eigenstate groups. So we can construct a whole family of eigenstate groups according to this correspondence. Since I'm only have 2 minutes left, let's just give like the simplest example. Let's take one out of this. So suppose we have some symmetry G, and then we want to classify the eigenstate group, which means that we want to classify phases of symmetry G times C. For example, in one dimension, if it's a Bosonic phase, it should just be classified by the second cohomology group, which you can use the Kuhn's formula to show it's the same as. So this is just the regular stationary SVT in one dimension. But what is this? So this is the same as the invertible charges of G. Or another way to say it is for 1D representations of G. So the interpretation is you take your 1D system, you do your Floquet evolution. But imagine that you do it with boundary. And what happens? Basically, you pump charge. So you do your Floquet evolution. If there was no boundary, because you're talking about eigenstates, it would just go back to itself. But with boundary, something non-trivial can happen. So what happens is, in the presence of a boundary, you pump a charge to the boundary. So you get some more charge over here and some less charge over here. So this chi is a 1D representation of G, which describes the charges of G. So the interpretation of this extra piece is that going through the cycle actually is pumping charge. Yeah. And so this interpretation turns out also works in higher dimensions. If you have a 2D system, you have a 2D system, and you do a Floquet evolution with boundary, you can pump a 1D SVT onto the boundary, and so on in higher dimensions. And then another example, I guess this is the last one I will say, if you have an intrinsic topological order, for example, your phase is a toric code, so toric code doesn't even need any symmetries to take it to its entity to 0. So what is it? And then we can talk about SETs for the toric code with discrete time translation symmetry. So what can the symmetry do in toric code? It can exchange the anion time. So E can go to M and M can go to E. So you can have a Floquet topological phase where if you have just the ground state or just the toric code state, it goes to it goes to itself. But if you just put an E charge at one point, and you do the same Floquet, the E will become an M. So it's an example of a Floquet topological phase. Okay, let's stop there.
More questions? Go first.
So is this pumping thing also true for the free-fermion case as well?
Well, there are examples of free-fermion phases which are characterized by pumping, but the one I talked about in the beginning of the talk is not characterized this way. It is not this is an example of phase which is not characterized by the eigenstate loop, so it has a different kinds of invariance.
On that though, the new equals 2 state, I thought largely pumps charge along its 1D boundary, right? So then if you have a boundary of that boundary, a 0D point, you'd have the same buildup. I guess I'm surprised that it doesn't show up immediately in this classification. So do you see what I see why it would?
Well, so it's kind of a different thing because you have to sort of dimensionally reduce twice, if you like. Or first you go to the boundary and then you go to the boundary and say what charge gets accumulated. So in that sense, it's not covered by this classification this year. It's dimensionally reducing once. It's something a bit different.
So for this pumping interpretation, what if G is mu1?
Well, G is U1, I mean, these general arguments about eigenstate loops are fine for any symmetrical. But realizing these phases of many-body-localized in a many-body-localized system is a different story. Like you might not be able to, given an eigenstate loop, actually realize it in some MBL system. And MBL, because we can talk about this pumping phase, like the class A one, for example, it's if you consider the MBL version of that, it's not characterized by its eigenstate loops, which are actually trivial. It's characterized by something different. And if you try to realize just a non-trivial eigenstate loop with a pumping of U1 in an MBL system, you can't do it.
Okay, so no more questions. Let's thank Dominic again.